So I'm gonna give a quick summary about MoreElectric aircraft technology, basically some features and motivations behind MoreElectric aircraft technology. I'm going to also talk about the importance of the technology maturity process that MEA will need to follow, and also talk about the comparison between traditional versus virtual test rigs that Ravi mentioned. I'm going to also finally touch base on the collaborative project that is going on right now between OPAL-RT and several OEMs involving Bombardier as well, and share some preliminary observations, challenges, and some strategies ahead. So the main MEA feature basically is to, as Ravi said, is to reduce hydraulics and pneumatic sources by using more electric loads, such as electrical air conditioning, electrical anti-icing systems, as well as electric braking, for example. And the purpose of it is this will allow us basically to use a bleedless power plant, so bleedless engines, bleedless APUs. And the idea behind that is obviously to have more performance and efficiency on board of the aircraft. So if we take a look between a traditional electric architecture and a MoreElectric architecture comparison, so we see that MoreElectric architecture will provide much more electrical power actually. So in the case of the Boeing 787, which is an example of a MoreElectric aircraft, compared to its predecessor, the Boeing 767, we see that it can generate up to 1 megavolt amps, which is roughly 4 times higher than the electric power on board of the Boeing 767. Also, a remote distribution to accommodate an increasingly usage of electric loads. If we take a closer look to the GDS, to the electric power generation and distribution system, we can see on a traditional generation system, such as the Boeing 767, we have basically 2 levels of voltage buses, the 115 volt AC and the 28 volt DC bus, with some electric converters such as rectifiers or TRUs. And as opposed to that, on a MoreElectric architecture, here we see much more voltage levels involved and much higher as well. So 230 volt AC bus plus or minus 270 volt DC bus in order to accommodate electric loads that will consume more power. And this is basically to control the losses on the wires on the network. We can also see in a MoreElectric architecture the usage of much more power converters that will feed those electric loads. Another key difference is that in the traditional electric generation system, the electric generators come with integrated drives that will basically control the output frequency on the grid to 400 hertz, whereas on a MoreElectric architecture, we have variable frequency generators, or VFSGs, that are directly coupled to the gearboxes of the aircraft engines, and yeah, so they deliver variable frequency to the network that can vary between 380 hertz and up to 800 hertz. Also, these generators can act as motors during start maneuvers in order to start the aircraft engines. So although the MoreElectric architecture is more complex, so why do we go for a MoreElectric aircraft architecture? So we have important drivers to go there basically, and among them we can cite weight, reliability, maintenance, and efficiency. And all 4 of them really have a direct impact on cost. So for example, for the weight, if we take the traditional IDG generation, we see that the generator comes with a CSD unit that controls, basically it's a mechanical drive that controls the frequency output to 400 Hertz. And this drive weighs a lot more than the generator itself and requires as well its own cooling system. So going to a more electric architecture will involve VFSG that will completely eliminate the need for such a drive, and so weight reduction obviously, but also an increase of reliability. As well, for the traditional setup on an aircraft, the bleeds of the engines and the APU and the start sequence are used to feed conventional loads such as hydraulic components and pneumatic components as well. Going to a more electric strategy will eliminate the use of those bleeds, therefore reducing the losses on the aircraft engine and also reducing the maintenance of such a bulky system by replacing it with an electric system. So we see that there are clear advantages to go to more electric architecture, but this comes with an important aspect to study. Some key points here. Now, since in a more electric architecture we use more power converters, so there is a need to study the thermal losses and also the cooling strategies that will be needed for such equipment. As well, since we have more equipment, more power converters, high switching frequencies, we need to study as well the power quality and the harmonics distortion on the overall network. So that's also an important aspect to look into. Also, in terms of loading, we need to understand, by adding more loads, we need to understand throughout the flight phases of the aircraft the electrical loading on the network, and this will help dimension the wires and the loads themselves. And finally, since we're using more components with more controllers interacting simultaneously on the network, we absolutely need to study the overall stability of the network on both steady state and transient operation. So this brings us to poll question number 2. If you can have a look at it for a few moments before I continue. Right. So we see that there are important study cases we need to do on more electric technology, and this brings us to the fact that a more electric technology, like any new technology introduction in aerospace industry, needs to follow a rigorous maturity process that will bring technology readiness levels, or TRLs, from basic conceptual designs up to flight-proven tests and eventually market introduction. So these TRLs that are widely used in the aerospace industry can also be mapped on a V process, on the traditional V process that you can see on the right. And this process is basically iterative in the sense that if we fail to reach a certain TRL level, we either need to go back to previous TRLs or even back to conceptual designs or functional requirements. And this is shown by the arrows that link the downstroke and the upstroke parts of the V process. Now, another important milestone that needs to be reached is TRL6, which basically features a prototype or a demonstrator in a high fidelity environment, and it's basically a turning point that will allow the development of the actual development of the technology, in our case, more electric technology. So typically, those demonstrators to reach TRL6 involve test rigs such as the image that you see here in the slide. So this is an example of the test rig that was used for the C-series aircraft Bombardier premises. And so typically those test rigs involve quite a huge number of equipment, such as pneumatics, hydraulics, electric wiring, which makes the installation fairly complex and also very costly. So the idea here is to basically go to virtual test rigs in order to ensure TRL6, where we would have all the plant models and controllers at the first step in a complete virtual environment. And then the second step would be to take the plant models, such as the models of the engines, the aircraft, electric systems, etc., and execute it on a simulation target. Whereas the controller models can be replaced by the actual controllers. This setup is what we refer to as a hardware-in-the-loop environment, and it involves the simulation execution in real time in order to interact properly with the actual controllers. To this setup, we can also add devices such as fault insertion boxes or mapping boxes in order to condition some signals. And the idea really is to have this setup replace the traditional test rig and meet as well the TRL6 level while minimizing the iterations of within the V process. So as key advantages here, we can cite that we need less hardware and equipment. Therefore, this has a direct impact on cost. It's also a very flexible solution because changes can be made much more easily than on traditional test rigs. Also, we have the capability to do some automated testing, and this is very important in the aerospace field. Plus, it's much more lower maintenance required than on the traditional test rigs. So this brings into context the project that OPAL-RT is actually involved in. So basically, it's a collaborative R&D project that is led by Bombardier Aerospace and involves several other aircraft manufacturers. And the objective of that project is to come up with a virtual rig simulator called MESIS as a TRL6 demonstrator. And the main objectives of MESIS are the study of power quality, control and protection, failure modes and malfunctions, also the interaction of electric systems between them, but with a strong focus on power quality. And the evolution timeline of MESIS, as shown on the right, is basically for MESIS to evolve in a fully integrated hardware-in-the-loop solution by end of 2020. In the integration phase of MESIS, the suppliers will provide models to OPAL-RT that will integrate them on a simulation platform, but also OPAL-RT will provide some models to fill in some modeling gaps, such as electric power converters or electrical machines. And what we look at here is the intended architecture of MESIS, that will involve basically aircraft model and ambient conditions block that will interact with power plant models such as the engines or the auxiliary power units. Also interacting with the electrical power generation distribution system, EPGDS, that will basically create the electrical power and provide it to electrical loads through typical power conversion units such as TRUs, inverters, etc. And then the next phase obviously is to bring that whole set of models into a real-time simulator that is provided by OPAL-RT. And the hardware architecture of such a simulator includes CPU boards and FPGA boards, and those equipment can be those boards can be scaled up to meet complex simulation needs. So within MESIS, we're going to have models that have slow dynamics, for example, and will need to be run and can be run on CPU. And also, we will have, on the other hand, models that will need to run on FPGA, because those models need to go to very small sampling times, because they involve, for example, inverters with high switching frequencies that can reach up to 35 kilohertz. So we see that there are quite some challenges that we'll need to face in terms during the integration phase of the models. One of them is co-simulation. Basically, what co-simulation is, it's basically we're going to get models from suppliers, and those models were developed on different simulation platforms, and we'll have to integrate them. We'll have to integrate all of them on a unique simulation platform, and this requires the development and the propagation of clear integration requirements and documentation to the suppliers. We'll also have to manage all the interfaces between those models, especially for large number of signals. And so the strategy here is to go with an automated generation solution, so that we minimize human error in dealing and creating and managing those interfaces. Also, we talked about models running at different rates. So this also implies the need to manage those models between them. And we need to come up with decoupling techniques to basically separate the models and say, okay, well, models that need to run on FPGA, we need to decouple them and run them at slower time steps, whereas models that need a slower time step, we can put them on CPU. So there are decoupling techniques that we could use. We have strategies for that. Also, it's important to know where those decoupling points will need to enter in order to have the least impact on the grid stability and also preserve accuracy. Finally, we'll have to deal with the model complexity. And if we take the example of the EPGDS, as Ravi mentioned, we will have a large number of contactors that we will need to account for, and basically the increase of that number will increase the computational matrices that will have to be computed. So the idea is here to use the SSN solvers developed by OPAL-RT to improve on that. And this is basically an example of an EPGDS with a matrix structure that we tested, and we were able to reach with those specialized solvers 60 microsecond time step. And just to mention that the loads were also decoupled and run on FPGA with a sample time of 300 nanosecond. So as a summary, MoreElectric aircraft becomes now a little bit more than a trend, and it becomes a computational reality that aircraft manufacturers need to follow. And so real-time simulation seems to be also an interesting option as opposed to traditional validation strategies, as it is a cost-effective option for more electrical aircraft technology. Also, modeling and validation of electrical requirements and quality and power quality analysis will also be an important aspect to look into. And although we see that there are some challenges ahead, we believe we're going the right way because we have specific tools and know-how that will help us address those challenges.